Welcome back to this series on graph theory. In the last video, we looked at k-connectivity, which was a measure of how connected the vertices of a graph are. In this video, we'll turn to the analogous concept for edges, which is called edge connectivity. Before starting, let's recall what it means for a graph to be k-connected. We say that a graph G is k-connected if first, the order of G is strictly less than k, and G minus some set x of vertices is connected for every set of vertices of G, with the size of that set being strictly less than k. Another way of saying this is that it's impossible to disconnect G by removing strictly less than k vertices from the graph. Notice that in the previous definition, our graph G could be k-connected for various values of k. So for example, G could be 1 connected, 2 connected, and 3 connected, but not 4 connected. So in practice, we're usually interested in the highest value of k such that G is still k-connected. And this value is called the connectivity of G. The connectivity, which we write kappa G of G, is the greatest integer k such that G is k-connected. For example, the connectivity of a disconnected graph is 0, and the connectivity of a graph which has a single edge between two vertices is 1. Now, instead of removing vertices from our graph, we could think about removing edges. So in this example, we could think about removing this edge between these two vertices, and that would disconnect the graph. And these thoughts lead to the concept of edge connectivity. Suppose that the order of G is strictly greater than 1, and that G without f is connected for every set f of edges, with the size of f being strictly less than L. Then G is called L edge connected. As we can see, this definition is pretty much analogous to the definition for k-connectivity, and if we want to distinguish more precisely between the vertex connectivity and the edge connectivity, we also would say k-vertex connected. The only difference is, of course, that we're looking at subsets of edges in the case of edge connectivity, while we're looking at subsets of vertices in the case of vertex connectivity. And there is also a difference in the technical condition that needs to be fulfilled in order for the definition to apply. In the case of vertex connectivity, we have this condition which says that k has to be strictly less than the order of G, and if we combine that with this stricting inequality down here, it means that the size of the set that we remove is less than or equal to the order of G minus 2. So we always want to have two vertices remaining after we remove our set x in order for this definition to apply. On the other hand, in the case of edge connectivity, we have this condition that we want the order of G to be strictly greater than 1. This has to do with the fact that if we have a graph with just one vertex, it won't have any edges, and so it'll be connected for any size subset of edges that we remove from it, which means that the one vertex graph would be L connected for any value of L. So we want to avoid this, and so we include the condition that the order of G has to be strictly greater than 1. Similar to the case above, we now go on to define the edge connectivity of a graph. So the greatest integer, L, for which G is L edge connected, is called its edge connectivity. and we denote it by lambda of g. So we have these two numbers associated to our graph. First, we have its k-connectivity kappa g, which tells us that we need to remove at least kappa g vertices if we want to disconnect our graph. And similarly, we have the edge connectivity lambda g, which tells us that we need to remove at least lambda g edges in order to disconnect the graph. At this point, we can now ask the question how these two quantities are related, and that will be what we'll turn to next. For this, let's consider the following two graphs. All right, so we could call this graph here on the left an octahedron, because it's exactly the graph that we obtain if we look at the vertices of the octahedron as the vertices of our graph and the edges of the octahedron as the edges of our graph. And here on the right, we have what we get if we glue two octahedra together along one of their edges. Now let's determine the edge connectivities and the vertex connectivities of both these graphs and see how they compare. Now, if we're going to disconnect the graph on the left by removing vertices, then we observe that any two vertices in this graph are connected by an edge except for these vertices here that mark a corner and one of the middle vertices. So because we're never going to disconnect two vertices that are connected by an edge by removing vertices, we need to focus on a pair of vertices of this type. We now see that for any other vertex in the graph, there's a path between the marked vertices that goes through that vertex. And moreover, that goes through that vertex directly. So in order to disconnect these vertices, we'll have to remove all other vertices in the graph. So that means we'll have to remove this set of vertices in order to disconnect the two white vertices. If we leave any one of them, there'll still be a path remaining. Because the octahedron graph is symmetric, there's three pairs of vertices that we could have chosen in the beginning, but all of these choices will lead to the same outcome. So in fact, the only way to disconnect this graph, with the fewest possible vertices, is by choosing these four. Hence, this argument shows that kappa g is 4. In other words, if we remove any less than 4 vertices, we can't disconnect this graph, and 4 is the largest number for which this holds, because we can remove 4 vertices and disconnect the graph. So this graph can't be 5 connected. Let's now turn to edge connectivity. So one easy way of disconnecting one of the vertices from the graph is to remove all incident edges to that vertex. For example, we could select these 4 edges here, and that would then disconnect this corner vertex from the rest of the graph. This shows that the edge connectivity has to be at most 4. So let's see if we can do any better. So the idea we're going to use is that when we disconnect the graph, we're going to divide it into 2 connected components. If we end up with more than 2, we've been inefficient. So what we'll get is some cut that cuts through the edges and that divides the graph into 2 connected components. So for example, I could cut like this, and then the vertices that are on the left of this yellow line would form a connected component, and the vertices on the right would form a connected component. And in fact, cutting the graph in this way is the most efficient way to obtain these specific connected components, because we're not removing any of the edges that are inside the connected components. So we can reduce our question to the question of whether we can create such a cut that creates two connected components that crosses less, strictly less than 4 edges. So we've already seen that we have a cut which crosses 4 edges, which is why the edge connectivity is less or equal to 4. And if we try through all the possibilities, you can see that no matter how we choose our cut, we'll cross at least 4 edges, which means that actually the edge connectivity of this graph is equal to 4. Hence, in this case, we see that the edge connectivity and the vertex connectivity of the graph are actually the same. In contrast, if we look at the graph on the right, we can see pretty much immediately that there's a very efficient way of disconnecting this by removing vertices, namely by removing the 2 vertices where the octahedra are glued together. If we get rid of those and all the edges that are incident to them, we're left over with these 2 connected components here, which are disconnected. So we have that the k connectivity of this graph, which we'll call h, is at most 2. And in fact, we can't do any better than 2, because one can go through each vertex and see if one can delete it and disconnect the graph, but this is not the case. So in fact, our k connectivity of this graph h is equal to 2. On the other hand, the edge connectivity of this graph, when we glue 2 octahedra together, remains unchanged and is still 4. Why is this? Well, it's less than 4 because we have the same cut as before, where we can just isolate one of the corner vertices by deleting 4 edges. Why is it at most 4? Well, if we disconnect this graph in such a way that one of the connected components comprises only vertices from one of the octahedra, so let's say this would be one of our connected components, and the other connected component comprises the rest, this would be C prime, then this would also be a cut in the original octahedron. So we know that this cut has to have at least 4 edges that it crosses. Hence, the only possibility is that our cut in the glued octahedron is not actually a cut in the original octahedron. But if we think about it, this isn't possible, because if we have one connected component containing one of the copies of the octahedron, which would be necessary in order for the cut not to be a cut in the original octahedron, then automatically we're creating a cut in the other octahedron. So in fact, any cut in this glued octahedron will induce a cut in the simple octahedron, and this means that the edge connectivity of the glued octahedron has to be at least 4. Hence we see that in the case of the glued octahedron, the edge connectivity isn't the same as the vertex connectivity, and it's actually larger. Moreover, we've seen that in both of these cases, the minimal degree of the graph is actually 4. Oops, I see I wrote a G here. Actually, this is supposed to be H. So the minimal degree of both the graph G and the graph H is 4. So we have that in these cases, the vertex connectivity is less than or equal to the edge connectivity, which is less than or equal to the minimum degree. And in fact, this is something that we can prove in general, and it'll be the content of our next proposition. It says that if G is non-trivial, then the connectivity of G is less than or equal to the edge connectivity of G, which is less than or equal to the minimal degree. Let's give a proof of this. We first consider this inequality here, which states that the edge connectivity is less than the minimal degree that a vertex has in G. So let's draw a picture for this. Let's say that we have a vertex V, which has a minimum degree. Then it'll have some edges going out from the vertex, and that'll be connected to the neighborhood of V. And now we observe that we can disconnect the graph by just removing all of the edges that are incident to V. This will leave V as an isolated vertex, and if G is non-trivial, so it has at least two vertices, then we'll have another vertex that's disconnected from V. Hence, we can always remove delta G edges and disconnect our graph. And this shows that the edge connectivity of G is less than or equal to the minimum degree delta G. Let's write that down. The second inequality follows from the fact that we can disconnect any vertex by deleting its incident edges. Now let's focus on the other inequality, and if we can prove this, then we're done with the proof. We first take some minimal set of edges that separate G. So let F, this is a set of edges, be a set of lambda G edges that disconnect G. Then F is a minimal separating set. This follows directly from the definition of the edge connectivity. So we know that G is lambda G connected, which by definition means that if we take a set that has less, strictly less, than lambda G edges in it, we can't disconnect G. And so this means that if F has lambda G edges, it's the smallest set, or one of the smallest sets that can disconnect G. This minimality will be important because we'll use it several times in the arguments that we're about to present. So what we want to show is that the K connectivity of G is less than or equal to the order of F, which we assume is the same as lambda G. So that'll show the inequality we want to show. We now have to examine several cases. So the first case is that G has a vertex that is not incident to any edge in F. At this point, let's draw a picture of what's going on. So we assume that F is a separating set, so it disconnects G. And so we'll have, in G minus F, we'll have two connected components, C and C prime. And the edges of F will be between these two connected components. So this is F. And now in case one, we're assuming that we have some vertex V, which is not incident to any of the edges in F. So as in the picture, we let C be the connected component that contains V. Here comes the crucial point. We note that the minimality of F implies that there are no edges of F that are internal to either C or C prime. This is because if we had such an edge, this green one, inside one of the connected components, then this edge isn't doing anything to separate the connected components from each other. So we could just as well remove this green edge from F, and we'd obtain a smaller separating set that still separates C and C prime. But in fact, F was minimal, so we can't have such an internal edge. Otherwise, this would contradict the minimality of F. With this added information that there are no internal edges that belong to the separating set F, we look at all the vertices in C that are incident to some edge in F. So that would be this red set I'm drawing in the picture now. So consider the vertices of C that are incident to F. Now, because no edge in F has both of its ends in C, we conclude that the size of this set is at most the size of F. Hence, there are at most F such vertices. And the important part is that these vertices separate the vertex V from C prime. Because if we have any path that goes from V to C prime, it has to cross one of these vertices because F is a separating set. So we found less than the size of F vertices that separate V from the component C prime. Hence, we can remove these vertices and we disconnect our graph. So in fact, the connectivity of G has to be less than or equal to F, the size of F in this case. And this is what we wanted to show for this case. If we don't have the first case, then we have case 2, which is that every vertex in G is incident to an edge in F. We now let V be any vertex in the connected component C of G minus F. So we have a similar picture as before. So we have a connected component C, and then we have some other connected component C prime, and there are edges of F going in between these two connected components. However, now every vertex in the graph is incident to one of these edges, so we have some edge V in the connected component that we choose. Now it's possible that V could also be incident to two edges, so let's draw that. We now look at the neighbors of V that are not part of an edge in F. So for example, we might have some vertex W that's also in C, which is a neighbor of V, but the edge VW is not in F. So consider neighbors W of V with the edge VW not being an element of F. However, by assumption, every vertex in G is incident to an edge in F. So actually, this W is the end point of another edge that's in F, which I'll draw like so. Now, because there are no internal edges of F in the component C, we have at most one neighbor W of V for each edge in F. So there is at most one such neighbor for each edge in F. So now we can count up the number of neighbors that this vertex V has. So we have the neighbors that are parts of F, so that are connected to V by an edge that it lies in F, and On the other hand, we also have neighbors in the component C, but we know that there is at most one of these types of neighbors for each edge in F. Moreover, these two types, they don't overlap, because we know that by the minimality of F, again, because there are no internal edges in C, all of the neighbors that are connected to V via an edge in F have to lie in the other connected component, C prime, and the neighbors that are connected to V via an internal edge have to lie in C. So let's say we have M such neighbors that lie in C prime. And now we know that none of these neighbors can be connected to one of the other types of neighbors via an edge in F, because they are already connected to V. So in fact, there is at most one such neighbor in C for each edge in F minus the edges that are incident to the vertices in M. Therefore, in total, if we consider both types of neighbors, we have that the degree of V, so the number of neighbors of V, is at most the size of F. Again, this is because each one of the neighbors of V corresponds to at least one edge in F. Now, if there's some other vertex in G that is not part of the neighborhood of V, then we can just remove all of the vertices in the neighborhood of V and disconnect V from that other vertex. So that's if G is not equal to V union its neighborhood, then the connectivity of G is less than or equal to the degree of V, which we saw as less than or equal to the size of F, which is what we wanted to show. On the other hand, it might be the case that G is equal to V union its neighborhood for all V in the graph. If it's not the case for all V's in the graph, then because our argument was general before, we could just choose a V for which this is not the case and disconnect the graph as above. However, if G is actually the union of a vertex and its neighborhood for every vertex in the graph, then G is actually the complete graph, because every vertex is connected to every other vertex. And in this case, we can just explicitly say what the edge and vertex connectivities of the complete graph are. And we've seen in the examples that vertex connectivity is equal to the edge connectivity, which is just the order of G minus 1 in the case of complete graphs. So in this case, also the inequality that we want to prove, namely that the vertex connectivity is less than or equal to the edge connectivity, this holds in this special case. With that, we've covered all the cases that are possible, and in each case we've shown the desired inequality, so we're done with the proof. Before concluding, maybe let's review what we've seen. So we wanted to show that the connectivity of G, kappa G, is less than or equal to the edge connectivity of G, which is less than or equal to the minimum degree of G. We started by observing that this second inequality here just follows from the fact that we can disconnect any vertex by removing all of the edges that connect it to its neighborhood. So if we can prove the other inequality, then the entire thing will follow by transitivity. In order to do so, we selected a separating set of edges that had size lambda g, which implied that this separating set is minimal by the definition of edge connectivity. And now we want to show that actually the vertex connectivity kappa g is less than or equal to the size of the separating set that we chose. And remember, we chose this to be lambda g. So if we can show this inequality, then actually we've shown the desired inequality. We had to divide into several cases. And so the first case is that there is some vertex in the graph that is not incident to any of the edges in F. And in this case, we note that we can't have any internal edges, well, internal to the connected component that belong to F, because otherwise we would contradict the minimality of the separating set F. So in fact, every edge in F has to go between connected components. And we then saw that the vertices that belong to both the separating set, so that are incident to an edge in the separating set and belong to C, these also separate the vertex V from the component C prime. Now, because we don't have any internal edges of F in the component C, each of these vertices in C that is incident to F has to correspond to at least one edge in F. So the size of this set is less than or equal to the size of F, and we saw that this is a separating set of vertices, so in this case the connectivity of G has to be less than or equal to the size of F, which is what we wanted to show in this case. Now, if no such vertex V exists that is not incident to any edge in F, then we conclude that every vertex in our graph is incident to at least one edge in F. So we pick such a vertex V that's in a connected component C, and we look at its neighbors. So we know that V has to have at least one neighbor that is connected via some edge in F, because there's an edge in F that's incident to V. But by the minimality of F, these types of neighbors that are connected via edges in F have to live in some other connected component C prime. And let's say there are M of these types of neighbors. Now, V might also have neighbors that are in C, but these have to be connected via edges that are not in F. But we know that each of these vertices in C is also incident to some edge in F. Moreover, this can't be one of the edges that connects V to its neighbors in M. So what this means is that this collection of neighbors in C is actually less than or equal to the size of F minus M. Therefore, in total, V has at most the size of F neighbors if we combine both collections. And now we try to disconnect the graph by removing the neighborhood of V. This is only possible if there's some other vertex in our graph G that is not part of the neighborhood. Otherwise, we'd just remove all the neighbors of V, and we're just left with V, and a single vertex graph is connected. So we have to have at least one other vertex that's not part of the neighborhood. So if that's the case, so if it's possible to select V such that there's another vertex that's not part of the neighborhood of V, then we've shown the desired inequality, namely that the connectivity of G is less than or equal to the degree of V, which we saw above was less than or equal to the size of F. On the other hand, if there's no such vertex in our graph, then we conclude that our graph has to be complete. And in this case, we also know explicitly what the edge and vertex connectivities are of the complete graph, namely, it's the size of the graph minus 1. And in this case, these two quantities are equal. So in particular, we also have that the connectivity is less than or equal to the edge connectivity. Okay, so this concludes what I wanted to say about the general topic of connectivity and separating sets. And in the next video, we'll turn to a completely different topic, namely trees.